Hey guys, we're going to start chapter 9.7. And before watching these video notes, if you haven't watched the YouTube video that I linked, just like the first 10 or 10 and a half minutes of that video, it does a really nice job of visually explaining what we're about to do in this chapter. So the big idea here is we want to approximate values for functions like sine, cosine, e to a power, natural log of something. We want to be able to do that two different ways in calculus. In AB, which we're deeming the less cool way, but in AB, the only method you have to approximate a value would be to use a tangent line approximation. So if I want to approximate the sine of 9 pi over 48, which is close to 8 pi over 48, or pi over 6. I know the sine of pi over 6, but I don't know the exact value of the sine for 9 pi over 48. So I can come up with a tangent line approximation and say, well, 9 pi over 48 is pretty close to the point of tangency. So whatever if I use a line, here's a sketch here. If I use a line to maybe figure out what this point is, that's pretty close to what the actual point on the curve is. All right, so to do that, we need a point of tangency. So we need to know what is f of pi over 6. Our point of tangency is sine of pi over 6 is 1/2. And what's the derivative at the point of tangency? Well, f prime of x is cosine x. And then f prime of pi over 6. Cosine of pi over 6 is radical 3 over 2. So our tangent line approximation, our equation for that would be y minus 1/2 equals radical 3 over 2 times x minus pi over 6. So if I want to approximate the sine of 9 pi over 48, now I know it's about equal to radical 3 over 2 times 9 pi over 48 minus pi over 6. And then I would add this 1/2 to the right side of my equation. Okay, so whatever that approximately comes out to. This approximation isn't bad, but it might not be as good as it could be because, again, we're using a line to approximate a trig function, which is a curve. So now if you really do put this into your calculator and zoom in, like that, the value we get is awfully close to what the calculator approximated value is. But again, there's got to be a better way than approximating a curve with a line. All right, so what do we do? So the BC way is to use a curve, particularly a polynomial, to approximate a curve. Wouldn't it be better if I could get like an x squared or an x cubed or some sort of polynomial graph to sort of wrap around the sine graph to a certain degree and match up with more of the values so that more values are exact rather than just this one point of tangent? Okay, so what's the polynomial that we should use? It's called a power series. And we make it p of x is equal to, there'd be some constant term, a sub 0, and then there'd be some coefficient in front of the x to the first power, and then there'd be some other coefficient in front of the x squared. And I'm going to carry these out to maybe, I don't know, 4 or 5 terms, I think, for what we're about to do. This can go on forever, right? So I'm going to say plus dot 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 plus some nth coefficient to some x to the nth power, and it can go on forever. How do we figure out, we have the powers of x. How do we figure out what all of these coefficients are? So this goes back to that video that I linked. Each term kind of controls the behavior of the polynomial to make its first derivative, second derivative, etc., match what's happening with the curve it's trying to mimic. So for example, if we want it to have a high point at a certain place, we can make the first derivative 0. If we want it to be concave down at a certain place, that can affect the second derivative, etc. So let's just begin by saying, well, what is p prime of x? So take a look at p of x up there. If I take the derivative of each of these terms, and I'm going to do all 5 of them plus the nth term, the constant term would go away. I'd have a sub 1 times the x would become 1, right? Plus 2 times whatever a2 is times x, plus 3 times whatever a3 is, x squared. Continue on like this. 5 a sub 5 x to the 4th plus dot dot dot. So we'd be pulling the n out in front. We'd have some a sub n x to the n minus 1, and that would just continue on. What if our point of tangency, when we're using polynomials, we call that our center. What if that point of tangency or that center is x equals 0? All right, so back here when I did my tangent line approximation, the point that I plugged into f prime was pi over 6 because that was the point of tangency. So let's plug in 0. That's my point of tangency. What does this p prime of x become? If you plug in 0 for x, all of these terms drop away except for the constant term, a sub 1. All right, so, and what about back here? At that point of tangency, what is p of 0? If you plug in 0 here, all of the x terms drop away and you have a sub 0. So far we have, well, a sub 0, that constant term would be whatever p of 0 is. And a of 1 would be whatever p prime of 0 is. Let's take a second derivative. So take a derivative of the first derivative equation. This constant a1 drops out. I get 2a2, that x is gone, plus pull this 2 out. 3 times 2 is 6, a3 times x, plus 12 a4 x squared, plus, where am I? Sorry, 20 a5 x cubed, plus dot dot dot. I'm not going to continue on with the n terms because I'm kind of running out of room, but it'd be n times n minus 1, a sub n x times n minus 2. What if we plug in that point of tangency again? Evaluate the second derivative at 0. All of the x terms drop away. You're left with 2a2. Now remember, we're trying to figure out not what is the second derivative at 0, but in this series, what is a2? We figured out a0, a1. What is a sub 2? A sub 2, if I solve this little equation for a sub 2, I divide by 2. It's the second derivative evaluated at 0 divided by 2. Third derivative. We're going to take this to about 4 or 5 derivatives. Third derivative of x. The constant term drops away. I get 6a3 plus 24a4x plus 60a5x squared, etc. Evaluate the third derivative at 0. The constant term remains, and all others become 0. Solve that for a3. So divide the 6 to the other side. You get the third derivative evaluated at 0 divided by 6. Fourth derivative, we stop making tick marks and start just putting the number here. So that means fourth derivative, not to a power of 4. The fourth derivative would be 24a to the 4th plus 120a to the 5th times x, etc. The fourth derivative evaluated at 0, x terms would drop off, 24a to the 4th. All right, so a sub 4 would equal the fourth derivative evaluated at 0 over 24. Let's take a look at these coefficients. I could keep going, but let's stop here. Let's take a look at these coefficients. The constant term of our power series, what we're trying to build here, what are these a values? The power term will be whatever p sub 0 is, okay? And then the first coefficient, the one that goes in front of our x, will be the second derivative of p, evaluated at 0, divided by 2. And then it's the third derivative of p, that looks like a d, third derivative of p, evaluated at 0, divided by 6. Fourth derivative, divided by 24. There is a pattern here. If you notice, this is 2 times 1. This denominator is 3 times 2 times 1. This denominator is 4 times 3 times 2 times 1. Those are factorials, right? And the factorial matches what number derivative you're on. So on the next page, let's write our more general pattern here. So what is the pattern for any nth coefficient? It's the nth derivative of p, evaluated at 0, divided by n factorial. Now that's just for the coefficient. So let's put the whole polynomial together. This is called a Maclaurin polynomial centered at 0. Centered at 0, again, just means points of tangency at 0. So it's p of x equals p of 0 plus p prime of 0 times x divided by, technically it's divided by 1 factorial. I don't usually write that, but just to fill in a pattern. Technically this first term is times x to the 0 over 0 factorial plus the second derivative at 0 times x squared over 2 factorial plus the third derivative at 0, x cubed, 3 factorial, etc. Plus the nth derivative at 0, x to the n over n factorial. And you can keep generating terms infinitely, which is how this relates to our infinite series, by the way. We're going to talk about what happens when we add up infinite number of terms. Now, the Maclaurin polynomial is just a specific case of a Taylor polynomial. So Maclaurin is a specific Taylor polynomial centered at x equals 0. The Taylor polynomial is just x equals c is the center. So how does that change things? It's still just taking successive derivatives over successive factorials. The only thing that changes is instead of having all these derivatives evaluated at 0, you always evaluate at whatever the center is. So it's going to be p of x in general is equal to not p of 0, but p of c. So maybe c is pi over 6, or maybe it's 1, or whatever. Plus the first derivative evaluated at c. Now here's the other thing. This was just, the Maclaurin was just x squared, x cubed. This will be x minus c to the first power, technically over 1 factorial. Plus the second derivative evaluated at c times x minus c squared over 2 factorial. Now we can force the Maclaurin polynomial to look like this. We would just write it as like x minus 0 squared, but we don't normally write that. Oops, third derivative, I forgot. Third derivative evaluated at c times x minus c to the third over 3 factorial, etc. Nth derivative evaluated at c times x minus c to the nth over n factorial, and it goes on and on. All right, write the Maclaurin polynomial for f of x equals e to the x. What we're saying is come up with a polynomial that fits around the e to the x curve pretty nicely. And Maclaurin means that they're going to be the exact same value at x equals 0 or c equals 0, the center. And then the further you get from 0, the curves will match for a little while, and then they'll start to venture off. And we'll look at that on our calculator. All right, so what do I need to do to build this polynomial? I always kind of go about it a nice methodical process. So I say, all right, what is f? I always start with this. What is f of x? F of x is e to the x. And what I need is this first p of c will be f of 0. E to the 0 is 1. What's the first derivative of x? E to the x again. First derivative at 0 is going to be 1. You may quickly realize for this particular problem that every derivative is going to be the same, and therefore every derivative evaluated at 0 that I get is going to be 1. Okay, so what does that tell me? It tells me that I can go ahead and start writing the polynomial. So here's the cool thing. If you include an infinite number of terms, then our polynomial, our Maclaurin polynomial, will match exactly the same as the curve for e to the x. So here's how I'm going to write this. E to the x is equal to, not approximately equal to, but equal to, the first term, when I evaluate it at 0, is 1, plus, it's technically 1 times, we're centered at 0, so 1 times x over 1 factorial, plus 1 times x squared over 2 factorial. Now, I don't normally write the 1. I'm doing this for your notes, and you probably should too. And where did the factorials come from? Remember, when you're solving these f prime is 0, f double prime is 0, that's just this numerator piece right here. So the formula itself has this built-in derivative that we figured out on the previous page. So I'm just going to write plus dot 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 plus. It'd still be 1 times x to the n over n factorial. And again, if I write plus dot dot dot, meaning I intend to include an infinite number of terms, these are the exact same thing. So infinite terms means, instead of writing Maclaurin polynomial, means p of x equals e to the x exactly. If I say, well, let's only include the first 4 terms, then they're going to stray a little bit. So I'm going to show that here. So let's put in e to the x. And then let's type in the first 4 terms that I had shown there. I had 1 plus, now simplified, this is just 1 plus x, right? 1 plus x plus x squared over 2 factorial is just 2. I don't want to navigate through the menu with all the factorials. Plus x to the 3rd over 3 factorial is just 6. Let's just stop there. Say we just include those first 4 terms. Let's see how closely these two graphs match around 0. To get it around 0, I'm going to zoom 6 to get back to a standard window. There's e to the x. So see how around at 0 they're the same. And then let's go to the table. Oh, let's go to the table at 0. So they're exactly the same at 0. And then they stray a little bit. They're kind of close, right? And then the further you get from 0, the further they stray. Now, if I change my table set, let's count by like 0.1s. Sorry. You can see things are a lot more closely aligned. Like instead of jumping by 1 unit, we're pretty close. So anyway, looking at the graph, I think it's kind of cool to see like, wow, they really do match up for a while and then they stray off. And if I were to include a 4th term, then this term would come up and maybe include some more values that are closely approximated. That's what we're doing here. Eventually, we're going to memorize this e to the x. I'm going to stop my video. I'm going to stop my video here because I've got some students coming in a minute. So make sure that you watch the second part of these video notes to get the full day's worth of notes. All right.